Okay. So let's see here. Okay. So I guess this is, oh man, section 1.2 continued. Only because we are just briefly going to talk about the average rate of change, which you've probably seen at some point. It's kind of the beginnings of calculus. And so we're just going to touch on it and then get out, because we shouldn't be doing this without calculus, but it's good to have seen it, I guess. So the average rate of change of a function is just a way for us to figure out what even a non-linear function might look like, right? So a non-linear function could be, you know, like a sine curve or something like that, right? Where we've got this non-straight line, right? And so the average rate of change, oh man, that's annoying. I feel like it's still there though. Yeah, it's like, I don't know. That's 0, I guess. All right, so the average rate of change of a function gives us an idea how a nonlinear function behaves over some interval. So the average rate of change of a function gives us an idea of how a nonlinear function behaves over an interval. Behaves over an interval. Oops, got extra sloppy. So we're going to do the formal definition. So we're going to let f be a function. Be a function defined on the interval in square brackets a comma b. So on the interval from a to b inclusive, period. The average rate of change, of f over the interval a, b is defined as, have you guys seen delta notation? Change. Okay. So delta f of x over delta x, which is just the change in the function, right? Which, if you're thinking about your x and your y coordinates, right? So it's the change in y over the change in x. Not that crazy. So, but we can rewrite it as f evaluated at b, right, minus f evaluated at a over b, which is the x at the second point, minus a, which is the x at the first point. This is essentially rise over run, right? So this is the slope what we call the secant line. So it just connects the points A f of A to A or B f of B, right? Connects those points and figures out, okay, between those 2 points, if I drew a straight line, right? Remember, we don't have a straight line anymore. So we're trying to figure out what it looks like. So if we draw a straight line, then we can have some idea of what that function looks like in that little interval, right? A, B. Okay? And then what we do is we break up our curve into little tiny straight lines, right? And so geometrically, the average rate of change is the slope of the line. This is called the secant line. It's not important, but containing the point A f of A and B f of B. But, it all fit on one screen for once. So what we were saying, right, is that essentially what we're doing is we're examining the behavior of this kind of whatever function that we have, right? It can be some sort of a kind of Ogopogo style function, right? And if we can break it up into little intervals and just look at little straight lines all the way along, right? We know how straight lines behave, and straight lines are easy to deal with, right? And so this is to say we can examine the behavior of a nonlinear function by considering small straight lines constructed, that doesn't say constructed, struggle city up here, constructed by connecting 2 points on the curve. On the curve. Right, and so got a page break here, so I'm gonna try to squeeze it in. But imagine if we have an X and a Y coordinate here, if we've got a function that looks like, well, let's take something kind of simple like this, right? What we're gonna do is, well, we know that this is increasing faster here and then it's sloping off, right? We can imagine that these are just made up by little tiny straight lines, right? And then here we've got a slope of 0, right? And so the slope keeps changing and changing and changing, right, of these straight lines. But that's what we're doing, right? And so we take a point A and a point B, figure out what the f of A and f of B are, and figure out the slope that way. And then we'll know how fast it's increasing at that point, or decreasing if you're on the downhill, right? That's fine. So what we've got here is, if we're looking at a straight line like this, let's say I've connected here and here, these 2 points, right? So I picked a point A and a point B. I've got f of A and f of B. Yeah.
It'll only ever be like an approximation because it's made up of straight lines. Right?
Totally. Yeah. Mm-hmm. And so if we move into calculus, right, we can take the derivative, and the derivative is the slope at a single point, right? And so, but all it's doing is it's moving those A's and B's closer and closer and closer together, right? And so this is kind of the start of it, right? Because we want to be able to know how things change, right? But yeah, totally. So you could put A and B really close together, and that would be a really good approximation, right? Whereas if you've got A and B kind of far apart, then yeah, not that good probably, right? And so, but yeah, so that's how that works. Cool. Any other questions? Then let's move into 1.3, which is absolute value functions. We've already seen absolute values, but now we're gonna dissect them. So we have already seen the absolute value function. Absolute value function in calculating the MAD, right? Mean absolute deviance or distance, I can't remember, doesn't matter. Right, where we took some point and then we subtracted the mean and then we took the absolute value, right, to make it positive. And we know that the absolute value essentially just makes it positive. But let's go through the formal definition, because it doesn't just drop the negative, right? It actually switches it to the opposite of the negative, right? And so the absolute value of a real number, x, denoted by x wrapped up in vertical lines, right? Vertical straight lines, is given by, okay, and we're going to do a piecewise function here. And so we've got the absolute value of x has 2 pieces. Have we seen piecewise functions before? Last class? Okay, phew. That's what I thought, but oh. Okay, good. So then it'll take the value negative x if x is less than 0. And it'll take the value positive x if x is greater than or equal to 0. I'll make a little note here that this negative x is just saying the opposite of x. which makes sense, right? If x is negative, so if x is less than 0, that's saying that, okay, whatever's inside these brackets is a negative value, then we take opposite of it, right, which is essentially just throwing a negative, which is going to take away that first thing. Yeah. Right. And if it's positive, then it just stays what it is. Oops. Oh, didn't change it. There. Say we need the absolute value of -3. Say we need the absolute value of -3. Right. So now we've got -3 inside the absolute value. -3 is less than 0. Right. So since x is -3 is less than 0, the absolute value of -3 is -3, which is 3. The graph of the absolute value, you might remember, it just looks like a V, right? And so if you're seeing something, some behavior that looks like a V, then you're saying, okay, there must be an absolute value in play, right? Because that's what they're going to look like. And so the graph of an absolute value function looks like a V. Okay. We'll come back to what the graph looks like later, but for now, let's just do example 3. So we didn't get to it last day. Oh, where is it? Here. But you have example 3 from that handout. Suppose a manufacturer needs to produce a 24-inch by 24-inch square piece of blah, 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 blah. I guess I'll read it soon enough, but. So you're producing a 24-inch by 24-inch square piece of particle board as part of a home office desk kit. Doesn't matter. How close does the side of the piece of particle board need to be cut to 24 inches to guarantee that the area of the piece is within the tolerance of 0.25 square inches of the target area of 576 square inches? Okay, so we know that to be within 0.25 of 576, right, we could have a little bit smaller than 576, right? No smaller than 576 minus 0.25, right? And no greater than 576 plus 0.25. Right? And so we will let x denote the length of one side. So it's a square, so any side. We let x denote the length of one side such that the area is x squared, right? If you had to find the area of a square, then you're taking x times x, right, if the length is x. So now we've got x squared. Okay. So that's our area. Right? And we have to get it within 0.25 of 576, right? It can be a little bit bigger or it can be a little bit smaller. And so the difference between our area and 576 has to be less than 0.25. And I'll throw in brackets here, in either direction, right? So we can show that with the absolute value, right? Because if it's larger than 576, right, we get a positive value inside there. If it's less than 576, we get a negative value, right? But either way, it has to be less than 0.25. So we get x squared minus 576. That's the difference between our area and 576. And we want to force it to be less than or equal to 0.25. Because regardless in which direction we're going, right, it has to be less than 0.25. Yeah. The trick to solving these absolute value problems, right, is to just replicate the negative version of this guy over here, right? Because what we're seeing is actually the difference in these areas has to be more than negative 0.25, right? So closer to 0 than negative 0.25, but less than positive 0.25, right? And so to solve these absolute value problems, to drop the absolute value, you're going to write them in an interval like this. We write from negative 0.25, x squared minus 576 is less than 0.25. You only want to do that, though, if you have the absolute value on its own over here, right? You don't want to have 2 plus the absolute value is less than or equal to 0.25. You'd have to move the 2 over to the other side of the inequality. Right? So you can only do it if you have the absolute value there alone. Yeah.
Did you only write the negative because of the assumption that positive is included in the absolute value?
Yeah, do you mean this negative?
No, sorry, the one up above. Like for the x squared minus 576, did you just leave it like that?
Yeah, because
x squared plus 576 is another equation.
Well, we could do, it could either be 576 minus x squared, right? Because we're talking about the difference between our target of 576 and our area, right? So it has to be x squared minus 576. So our area minus 576, how far is it? Or 576 minus x squared, right? 576 minus our area. What's the difference, right? A little note about inequalities is that as long as you're not multiplying or dividing by a negative, you can treat it as an equal sign, right? So I know no one likes inequalities, right? Less than, greater than, blah, 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 but we have to deal with them. So I'll just make a note here that we can treat less than or equal to the special case here, right? Or less than, greater than equal to, right? Any inequality as an equal sign as long as we are not multiplying or dividing by a negative number, because in that case, we must flip the inequality. We must flip the inequality. Guess I could rewrite that one. So that makes it a little bit more bite-sized. So if we rewrite what we had up above here, just so I can have it on the screen, negative 0.25 is less than or equal to x squared minus 576, which has to be less than or equal to 0.25. Now, just putting the brakes on if you find yourself multiplying or dividing, and then just check if it's negative, right? If you're doing it with a positive value, then it's fine. Okay. But if I'm trying to solve for x here, then I'm just gonna add 576, but to both ends, right? So it's, imagine you've got like an equal sign on both ends. Okay. So you get negative 0.25 plus 576 is less than or equal to x squared, which is less than or equal to 0.25 plus 576. Which is fair enough, right? What's this saying? This is saying that our area has to be between 576 minus 0.25 and 576 plus 0.25, right? You could have gotten here and avoided the absolute value signs, right? But we're practicing absolute values. Okay. So now we can take the square root of each of these sides, right? So now we're not just dealing with two sides, we've essentially got three sides, right? But we're trying to undo and find x in the middle. Well, I guess we can simplify here. You can do it in one step if you want. 576 minus 0.25 is 575.75, less than or equal to x squared, which is less than or equal to 576.25. Now, if we take the square root throughout, we get the square root of 575.75 is less than or equal to the square root of x squared, which is less than or equal to square root of 576.25. The square root of x squared, we can rewrite as the absolute value of x. And so the absolute value of x, because it has that, okay, well, if x was negative, then you have to take the opposite of it, right? And so instead of doing that plus minus, then we can just rewrite it as the positive, or sorry, the absolute value of the positive. the absolute value. Okay. So that's how I want you to start thinking about, if you're taking the square root, then write it as the absolute value, right, of x. And we get the square root of 575, so nothing in here changes on the sides here, 575, and the square root of 576.25. We know that x is going to be a positive value, right? Because we're looking at the square with roughly 24 inches on each side, right? And so we can apply that knowledge about x, that it's going to be positive. And so x must be positive. Positive. Okay. So if we take the square root of 575.75 as a decimal, right, we get 23.9947911, which is less than or equal to x now, just because we know it has to be positive, which is less than or equal to the square root of 576.25, 24.00520777. Roughly, but that's, with all those decimals there, it's fine. We can round these to 3 decimal places, 23.995 and 24.005. Therefore, the side of the piece of particle board must be between 23.995 inches, because it's in inches in the problem, so, and 24.005 inches. A tolerance of roughly 0.005 inches of the target length of 24 inches, right? Remember, we were aiming for 24 inches. So it has to be 24 inches, give or take 0.005 inches. Okay. Any questions about that one? No? So for graphing, we'll do it for the absolute value, and then we're going to have the same sort of setup for how to kind of visualize a quadratic function, okay, in the next section. But they take kind of the same format, right? And so I'm going to give you the general form of an absolute value function, and then tell you the key characteristics of it. Okay? So for real numbers, for real numbers, A, H, and K with a not equal to 0, the graph of capital F of x equals a times the absolute value of x minus h and absolute value plus k. Notice that this is just a very general form of any absolute value function, right? We could have x plus or minus some h. If it's x plus 3, for example, h would have to be negative 3, right? Question.
Yeah. Why should it not be x squared? Because like that's what we did about now.
Oh yeah, but that's because we were talking about the area, right? So the area with the length of x has to be, so the area is x squared.
Yeah.
But so here in general, we're just going to talk about how x minus or plus some number behaves for graphing. And that's all I'll get you to do. I won't get you to graph x squared minus whatever. Okay, and so we've got inside the absolute value, it's being multiplied by some value, and then we can add some constant or subtract some constant, right, if we have a negative k. So we've got the function, and it consists, remember we said an absolute value function, if you're graphing it, it's a v, right? And so it really is just a straight line here connected to another straight line, right? The mirror image. Consists of parts of two lines with slopes of plus minus a, which meet at a vertex, at the point h, k, right? So the x value is whatever h is in that formula, right? And the y value is whatever the k is in that formula. So the vertex is the point of the v. I'll draw it out here shortly. Actually, I'll do it right now. Let's say you've got some XY graph here. Then we can draw the absolute value of x. And here is the vertex. Right? So we've just got two straight lines. Well, my straight line wasn't that good, but on the left-hand side, right-hand side's great. And with the same slope, one's in the positive direction, one's in the negative, and they meet at the vertex. And the vertex from that formula is going to be HK. Okay. If A is greater than 0, so if A is positive, then in general, we've got this sort of behavior. The shape resembles just a V. Whereas if A is less than 0, right, then we have something that looks like XY I don't know, let's put the vertex up top here just because of how I drew it. Then you've got a V pointing downwards. So then the shape resembles just an upside down V. Moreover, the graph is symmetric about the line x equals h. The graph is symmetric about the line x equals h, which, if you think about where the vertex is at hk, right? So the x value of the vertex is at h, and the y value of the vertex is at k, right? But if it's v point is at h, then of course that's where the line of symmetry is. Okay. Put a box around this. See how much I can get in there. Ooh. Okay. So now, sketching, or rather, if you were working backwards, right, and you see some sort of behavior, right, because that's going to be where you're coming from, where you see some sort of behavior, then the first thing that you're going to say is, whoa, that looks like an absolute value might be involved, right, if you've got this kind of V behavior, right? And so, and then you're going to look at, okay, well, where's the vertex? And then you can build up your function, right? Because the reason you're using math is to model behavior, right? And so you're seeing some sort of behavior, and then you're saying, oh, that looks like an absolute value function. If I know how the absolute value function behaves and I know where the vertex is, right, then I can build an approximate model for this. Okay. So let's do a quick example. If we just have to sketch, so nothing crazy here, f of x is the absolute value of x plus 3 and then plus 2. If we're comparing it to way up here, f of x is a times x minus h plus k, right? Compared to f of x is a times x minus h, oops, absolute value, plus k, we see a is just positive 1 in our case. Right? H must be negative 3, right? Because in order to get x plus 3 out of x minus h, h must be negative 3. And k must be 2. Easiest thing to do is to find the vertex, right? Where is this thing kind of hinged at? So find the vertex. The vertex is at the point in general, h comma k, which in our case is at negative 3, 2. Next thing we're going to look at, okay, is whether it's pointing up or down, right? A is 1, which is positive, right? So we know that it's going to be pointing upwards. Okay. Our graph must be pointing upwards since A is 1, and then I'll just say is greater than 0. What's it also telling us, right? That the lines that meet at -3, 2 have a slope of 1, right? So they each have a slope of, well, plus minus 1, right? Positive on the right-hand side and negative on the left-hand side. We know the lines that meet at -3, 2 have slopes of plus minus a, which in our case is plus minus 1. So if we're just sketching it out, because I know that it's opening upwards and my vertex is at -3, 2, that's why I'm giving myself more room on the second quadrant. It's been a while. 1, 2, 3, 4. Okay. So if we just put imaginary lines here, 1, 2, 3, 4. 1, 2, 3. So then at -3, 2 is the vertex. So -3, 2, that's the vertex. And we know we've got this upward activity. To draw a straight line, you only need 2 points on that line, right? Which I'm feeling pretty sure that we talked about last day, right? To draw these straight lines, we only need 2 points on that line, and then we can connect them and extend the line, well, for as long as we need to. Okay. So in this case, right, to draw the lines leading to -3, 2, -3, 2 is a point on each of these lines, so we just need to find 2 more points. We need to find 2 more points. And I'll write in brackets 1 on each line. Okay. So what we can do is, well, the easiest thing to do is just to let x be 0, right? Figure out where it crosses the y-axis. We see that one's going to be crossing the y-axis. And so f of 0 is the absolute value of x plus 3 is end of the absolute value plus 2, which is the absolute value of 0 plus 3 plus 2. The absolute value of 3 is positive, so it's just the positive of it. 3 plus 2, which is 5. Okay. So over here, at x is 0, we know we have to go to 2, 3, 4, 5, let's say. extend my line. Didn't give myself enough room. That's all right. We're just sketching, right? So then here at 0, 5, that's a point on the positive slope. Yeah.
For the initial equation, values a is 1, h is -3, and k is 2.
Mm-hmm.
They used assuming that a is x.
Yeah, so here, I'm just comparing this setup to this setup.
Okay.
Right? And so, okay, comparing this, we've got 1 out here. So a is 1. To get 3 here, positive 3, h has to be negative 3, and so on. Right? So we're just comparing. Okay, so now we've got 2 points on the upward slope point, or this upward slope line. So we can just connect those, ending at the vertex, right? And so we've got here. So we've got this point at 0, 5. Now, it doesn't matter what point of x you do next, right? But you do want a point that's on this line, which you know has to be on this side of x, right? So you have to pick an x that's smaller than negative 3, right? And so, but you can pick any value of x. And because I only drew to 4, how about we do 4, or negative 4, sorry. We can pick any value of x as long as it's, it shouldn't contract, as it is. To the left of negative 3, 2. So let's find f at negative 4. F at negative 4 is the absolute value of negative 4 plus 3 and absolute value plus 2, which is going to be negative 4 plus 3. It's the absolute value of negative 1 plus 2. In practice, right, if we've just got this value and the absolute value, we know it's just going to be 1, right? But really what you're doing is you're saying, oh, the value inside is negative, and so I have to take the negative of that value, right? Going back to that piecewise function we looked at. But in practice, it's just going to be 1 plus 2, which is 3. And so we've got a point at negative 4, 3. So if we draw negative 4, 3 on my kind of shoddy graph here, negative 4, 3, I can connect these lines ending at the vertex. I'm gonna miss the mark there, but we're just sketching it. Cool. What is the domain? Domain of f of x. The domain for any absolute value function is going to be just negative infinity to positive infinity, because even though we're looking at a very small area here, those lines continue and continue and never end. right? And so the domain is going to be negative infinity to positive infinity. How about the range? The range is what values of y can we take on? And so we know it takes on, it starts here at y equals 2, and then it just keeps going and going and going, right? It includes 2 because it's on both of these lines. So we do a square bracket from 2 up to positive infinity. Round bracket. So the square bracket is inclusive, so it includes 2. And then whenever we're talking about infinity, you're going to have to use round brackets because it's not a number. Right? And so I guess it's up to, but not including infinity. Fair enough. Yeah, so you could say f of x is greater than or equal to 2, right? Or you could write f of x is greater than or equal to 2. That's fine too. Okay. Any other questions about that one? No? All right. Then let's move into quadratic functions. 1.4 is quadratic functions, which we've actually already worked with, right? But we're gonna dissect it a little bit and do a little word problem and then talk about, or I guess we start with talking about how to graph it just as a follow-up, right? But it behaves the same way. So I'm going to give you the general form of a quadratic function. And then you'll be able to sketch it, or at least if you see some behavior, right? You've collected data and you're seeing some sort of behavior, then when you see this parabolic shape, then you know you've probably got a quadratic function on your hands. A quadratic function, or a quadratic, is a function, let's say, is a function of the form f of x is ax squared plus bx plus c. So as soon as you have something like ax squared plus bx plus c, where a, b, and c are just the coefficients, or c is a constant, where a, b, and c are real numbers, with a not equal to 0, how come a can't be 0? Well, if a is 0, this goes away, and then you just have a straight line. And so, and if b is 0, then if a and b are 0, then you have a constant function, right? And so we're just kind of building up from the most basic functions. So with a not equal to 0, and again, just like the absolute value, and I mean, quadratic functions and absolute value functions behave kind of similarly, right? Because they've got this V or kind of rounded shape. But the domain of a quadratic function is negative infinity to positive infinity. So it has the shape of a parabola. So just again, X and Y, most general form. So the shape of a parabola, and again, kind of this lowest point is called the vertex. So same kind of, I guess, recipe as before, right? If we break down a function, or actually, you know what? Because we're going to talk about the general and the standard form. Let's do that first. A quadratic equation can be written, I said equation, but let's say function instead. Doesn't matter, but equation has an equal sign in it, and I don't want to necessarily have that. A quadratic function can be written two ways. Suppose A, B, C, H, and K are real numbers where A is not equal to 0. We can write it in the general form which has the form f of x is ax squared plus bx plus c, where the vertex is the point negative b over 2a, and of course f at negative b over 2a. Kind of nasty, right? But that's how you find the vertex, right? So at least if you see something in the general form, right, then you know where the vertex is, and then you can kind of go from there. Or the standard form, I'll ditch this page break here. Standard form, which looks like f of x is a times x minus h squared plus k. That looks really similar to the absolute value function that we were dealing with. Right? Where the vertex is the point HK. So if we've got the general form and the standard form, we can move between the two, right? We're not going to do that because I'm worried about time, but you can, right? You can move between the two functions, right? They're the same thing. They're both quadratic equations, just written in different forms, right? And regardless of the form that you have, right, you can probably easily get to the general form or the standard form, right? And then you know what the vertex is. Okay. Put a little square around this here. I didn't put a square around this, but I will. Everything's squared up here. So we already know how to find the vertex. Okay. Let's talk about some other properties if we had to sketch a graph. Right. So to sketch a quadratic function, we still have to introduce, you know, all the rules. A, H, and K have to be real numbers, blah, blah, blah. So for real numbers, A, H, and K, with A not equal to 0, of course, the graph of f of x equals A times x minus h squared plus k, right, using that same setup, essentially, as before for the absolute value, is a parabola with vertex hk. Same deal, right? If A is positive, then we've got this upward parabola. If A is negative, we've got this downward parabola. And so if A is greater than 0, the graph resembles a U, right? Or like this. If A is less than 0, the graph resembles this upside down U. And same deal, right? The axis of symmetry is going to be at x equals h, right? So where they mirror each other is at the x value of the vertex. So moreover, the vertical line x equals h is the axis of symmetry of the graph y equals f of x. So those are the rules of the game for quadratic functions. And so as a little example, what if I ask you to sketch the graph of h of t, oh, I'll put it on the next line here, of h of t is -2 times t minus 3 squared plus 1. All right. This is in, I always mix them up, the standard form, right? General form, standard form, right? Yeah, and we've got a negative out front, so we know we're gonna have this downward point. So we already know a lot about what this thing looks like, right? We know we've got a negative parabola, so a downward facing parabola. We also know that the vertex is gonna be at HK. And so if we're translating this here, compared to f of x was a times x minus h squared plus k, we know that a in this case is -2, h in this case is 3, and k in this case is 1. So the first thing that we can look at, well, we kind of log that we're going to have a downward facing parabola, but let's find the vertex first. The vertex is at HK, which in this case is going to be at 3, 1. And since A is -2, which is less than 0, we know our parabola is facing down. So just some idea. If we kind of start with a sketch like this, got our x and our y-axis. In this case, we've got t and h of t, right? T and y is h of t. Right. But whenever I see a function, I just put the independent variable on the x-axis and the dependent variable on the y-axis, and then I just kind of ignore them, right? T, h of t, x, f of x, it doesn't matter. Okay. So just as a quick here, 1, 2, 3, 4, let's say. 1, 2, 3, 4. I know I don't need more, so. We can sketch our vertex, right? Our vertex is at 3, 1. Oh, boy. Oh, and I will clean this one up. I'm sure your graphs are beautiful. Mine are not. 3, 1. Right, when x is 3 and y is 1. That's what we know so far. And we also know that we're going to have some sort of, it's going to look kind of like this, right? If we want to know exactly where these points are, we can do that, right? We've already solved for the zeros, which is where it crosses the x-axis using the quadratic equation. Right? And so we can solve so this value and this value. Whee! We can solve for these values. Oops. By finding the zeros. And so find the zeros. I mean, yeah, you could factor this and find the zeros that way. For me, I just always just go straight to the quadratic equation. I don't really see the point in trying to factor, and then you have to check your work, and then, oh no, I did it wrong, and whatever, right? And so, and it might just be that I don't like factoring, right? But if you like factoring, that's great. But I don't. So we have to find the zeros. And so whenever I have a quadratic equation, I'm just going to go ahead and use the quadratic formula. So we can find the zeros using the quadratic equation, which says that x, so the values of these x are going to be negative b plus minus the square root of b squared minus 4ac over 2a. We worked with this one already, right? Where we had to find the zeros. It does mean, right, assuming f of x is of the form ax squared plus bx plus c, right? Does mean that we have to expand our function, right, to get it into the general form, from standard form to general form, right? But that's okay. So h of t was negative 2 times t minus 3 squared plus 1. So I've got negative 2 times t minus 3 times t minus 3 plus 1. I always just write them out like this, because then I find it's easier to just look and see how to FOIL it out, right, and how to expand this. So I get negative 2 times t squared minus 3t minus 3t plus 9, right? Negative 3 times negative 3 is positive 9, and then plus 1. So I have, well, I can simplify inside, so I can do negative 2 times t squared minus 6t plus 6t, 60. Bringing that negative 2 inside, just being careful that you keep that negative. And so you get negative 2t squared plus 12t minus 18 plus 1. Okay. We can just simplify them, negative 18 plus 1. So we get negative 2t squared plus 12t minus 17. So now we have A is -2, B is 12, and C is -17. So solving for x, or the zeros, right, the values of x when y is 0, I have -b plus minus the square root of b squared minus 4ac over 2a, which is going to be -12 plus minus the square root of 12 squared minus 4 times -2 times -17 over 2 times a, which is -2. 12 squared. So I get -12 plus minus 144. And then I've got minus 4 times -2 times -17 minus 136 over -4. 144 minus 136 is 8. So we've got -12 plus minus the square root of 8 over -4. So x is -12 plus the square root of 8 over -4, and -12 minus the square root of 8 over -4. Of course, you can simplify these, but I'm just going to convert them to decimals anyways, right? Do an approximation. When y equals 0. Therefore, the parabola crosses the y-axis at 0. Oh, sorry, not 0. Y is 0, not x. At -12 plus the square root of 8. Okay, so here we go. So, oops, still getting used to this calculator. -12 plus the square root of 8, and then divided by -4. 2.2928932190. And same deal, -12 minus the square root of 8 divided by -4 as a decimal, 3.707106781, y is 0. So now we know, and we can sketch out where those points are, right? Another kind of check-in point that we could do is, where does this line cross the y-axis, right? And so that's just when x is 0. So what we can do is we can plug in t equals 0 in this case, right? X equals 0. To find the point the parabola crosses the y-axis, we can solve h of 0. I'll just put in brackets, let x equal 0. H of t was just a reminder. Now, of course, doesn't matter which one you prefer. If you prefer h of t is this, right, or h of t is this, you should really hopefully get the same answer, right? They're the same thing. And so it doesn't matter which one you use. I'll use this one just because it's only got one t, right? So I only have to use 0 once, not a big deal, but. So h of t is -2 times t minus 3 squared plus 1. So h of 0 is -2 times 0 minus 3 squared plus 1. -2 times 9 plus 1 is -18 plus 1, which is -17. So now, let's see if I can draw axes that'll accommodate this. Maybe up here. I need y going all the way up down to -17. I don't think I managed. Unless I make each of these worth 5. Which I can do. How about that? -5, -10, -15, -20. Very approximate. I guess I should have the same scale on the x-axis. Don't have to, though. But let's just do 1, 2, 3, 4, 5, 6. You'll see why I went to 6 in just a second. Okay. So let's start with that vertex. The vertex we said was where? At 3, 1. So kind of down here. My huge y scale screwing us up. But then I also have points where it crosses the x-axis at 2.29. 2.29, so let's say here, 2.29 and 0. And the other one was 3.71, let's say. 3.71, let's put it here. And 0. And I also know that it crosses the y-axis, and this is the one that threw us for a loop, here at 0, -17. So now, what color do I use? Pink, I guess. We can just connect these. Remember, we're just sketching. didn't do a very good job. But if we highlight here, we know that our axis of symmetry is here at x equals 3. And so another point that we know is actually that, okay, well, here at 3, right, we're 3 away from the y-axis. And so, and that puts us at -17. If this thing's behaving the same way, but on this side, right, if we go 3 up from 3, right, that's x is 6, then we know that we should have a point here at -17 for our y, right? And so this one needs to get kind of smushed over a little bit. Yeah? So let's do that. So I'll draw the point and then I'll redraw that outer one. Roughly here at 6, -17 by symmetry. So now I'm aiming for, oh boy, okay. Close enough. So this is the graph of h of t is -2 times t minus 3 squared plus 1. You can check that using Desmos if you want, but we won't have time to. Okay. So, any questions about that one? No? Let's do a final example. I'll paraphrase it, but it is really funny. So much to Donnie's surprise and delight, he inherits a large parcel of land in Ashtabula County from one of his, and then in brackets E, and then strange, and then brackets D. So strange but estranged relatives. So the time is right for him to pursue his dream of raising alpaca. Here's the problem though. So he wishes to build a rectangular pasture, so shaped like this, and estimates that he has enough money for 200 linear feet of fencing material. So we've got this restriction of 200 feet of material. That's all we can use. If he makes the pasture adjacent to a river so that no fencing is required on that side, what are the dimensions of the pasture which maximize the area? Okay. And so let's do this example. Oops, that turned out really bad. Donnie, with an IE, I guess, wants to build a rectangular pasture. Pasture where one of the sides is the river, which just says no fencing, right? He can only afford 200 feet of fencing. What are the dimensions of the pasture which maximizes the area? Dimensions of the pasture which maximizes the area. And then, of course, what is the maximum area? What is the maximum area? If an average alpaca needs 25 square feet, how many alpacas can he have? How many alpacas can he buy? So the most common example of quadratic functions is in economics, right? Because we've got this kind of parabolic shape. And so, yeah, all of these make up your profit function, right? But you always want to maximize your profit function, and that's at the vertex, right? So at the maximum peak of this thing, right? And so we're going to build something similar, right? Where we can have all these different shapes, right? But only one of them is going to maximize the area. Okay. So if we've got, let's draw the situation first. So here's the river. And he wants to build a fence like so, just arbitrarily like this. It's a rectangle where we're going to let this side be W, and so this side must be W as well. And this side has a length L. Then the area must be the width times the length. We also know that the total fence that we can have, so W plus L plus W, has to be 200 or less. So we know that W plus L plus W has to be less than or equal to 200. Because we're trying to maximize this thing, right, we should probably just let it be 200. So since we want to maximize the area, right, W plus L plus W, we can rewrite as L plus 2W. L plus 2W, we're going to force it to be 200. Right? We want to use up all that fencing. Okay. Here, recall that the area is the length times the width. Trying to figure out what the area is, right? But essentially here you've got two equations, two unknowns, right? So you've got the system of equations, and what we're going to do is we're going to solve, since we don't know what the area is here, right? What I'm going to do is I'm going to solve for either L or W up here, and then plug them into there and have an area function, right? Because that's what we're hoping for. And so it's easier to solve for L, so that's what I'm going to do. So we can solve for L. We can solve L plus 2W equals 200 for L. Right? So L is 200 minus 2W. and substitute L equals 200 minus 2W into A is L times W. So now A is 200 minus 2W times W. This yields the area as a function of W, right? W is in there. We can plug in any W and figure out what the area is. Of course, you could go through and just pick different values of W, plug them in, and then see if you find the right option, right? But we can rewrite this as A of W is, and I'm gonna just expand this out a little bit. So 200W minus 2W squared, or rewriting this just with the decreasing powers, negative 2W plus 200W. A here is negative, right? So we know we've got this downward facing parabola. Downward facing parabola. Okay. This is in, well, I keep mixing them up, general form, which, so this is in general form, which has a vertex at, remember that big one, negative b over 2a, and then f evaluated at that point, f at negative b over 2a. Therefore, the vertex, right, is at negative b, which is 200, over 2 times a, which is negative 2. And then I'll just do f of, or sorry, a of, our function's called a because it's the area, doesn't matter. A at negative 200 over 2 times negative 2. Okay. So negative 200, negative 200 divided by negative 4, that puts me at 50 and a at 50. So this is where it's helpful that we have this downward parabola, right? And so we know that the general shape of this thing looks like, so here's W, here's A of W, has got at the point 50, A of 50, whatever it is, it's going to look like this, right? And so this is the maximized area, right, at that point. So we know when the width is 50, we can solve A of 50. A of 50 is, well, what did we say? A was negative 2w squared plus 200w. Negative 2 times 50 squared plus 200 times 50. 50 squared times 2, negative 1, 2, 5, 0. 1, 2, 3, 4. 1, 2, 3, 4 plus, and then 200 times 50. I did it, but I'll go back. 1, 2, 5, 1, and then 4 zeros. 1, 2, 3, 4. 200 times 50. What the? That doesn't make sense. Why is it negative? It's 951. Oh, I see. I didn't do something right here. Hang on. 50 squared times 2. Yeah, that's weird. No complaints, though, huh? Negative 5,000. 200. Oops. 200. Oh, man. 200 times 50 is 10,000. 5,000. I'll check that out. All right. So good luck on your quiz. See you guys on Thursday. We're going to do the test 1 review. I'll bring printouts of the practice test, but I'll post them. I'll post it on Moodle. So if you want to have a look and try it, then you can do that. All right. See you later, alligators. No, on Tuesday.
Oh, okay.
Yeah.
I was just gonna